Hello everybody. Let's start with a little throwback question, a little memory down memory lane of thermodynamics. Why does hamburger have lower energy than steak? Why does hamburger have lower energy than steak? The reason hamburger has lower energy than steak is because it's in the ground state. Very good. Ho, ho, ho. Merry Christmas, Happy Holidays all. I'm Mr. Rast, and this is the Christmas special of our lessons. This is going to be about ionic bonds. So, to understand this, it does take some a little bit of foundation of what we've been talking about before. And we've talked about how to predict the charge of ions. We talked about electron configurations. And so let's go kind of back to what we've learned before. What would be the easiest way for magnesium to reach a noble state? Would it be to gain or lose electrons? So here's magnesium here. Would it be easier for magnesium, noble state is over here. Would it be easiest for magnesium to gain 1, 2, 3, 4, 5, 6 electrons to get here? That would make it -6 because it gains 6 negative electrons. Or would it be easier for magnesium to lose 1, 2 electrons and become +2? And yes, it would be much easier to lose 2. And magnesium, when it becomes an ion, a stable ion, I should say, is Mg2+. What would be the easiest way for sulfur to reach a noble configuration? So right here, sulfur. Would it be easiest for it to lose 1, 2, 3, 4, 5, 6 and become +6? Or would sulfur gain 1, 2 and become -2? The correct answer is it would gain 2. So this is review. If you need more practice with this, please go back a few topics and review how to predict the charge of ions. So if we note, if we note here that +1 charges or 1+ charges, these guys all reside in the first column here. So the alkali metals, or the alkali metals are family 1, lithium, sodium, potassium, rubidium, cesium, francium. If you notice, these guys here are all +1. Look at +2 elements. It would be really handy if, while you're watching this video, you have a periodic table next to you. If you look at barium, beryllium, calcium, magnesium, strontium, these elements are all +2 when they become ions, and they're all located in the second family. These are the alkaline earth metals. Aluminum becomes +3 when it becomes an ion, and the reason is, again, let's take a look here. The reason aluminum becomes +3 is because aluminum is here. It could be your noble gas configuration by losing 3, 1, say it's number 13, 1, 2, 3, and getting this configuration, and losing 3 electrons makes it +3. Or it could gain 1, 2, 3, 4, 5. So it's much easier to lose 3 than to gain 5. That's the way I like to remember it. Everybody in this row is +1. This second column is group 2. These guys are +3. Carbon, silicon, these guys could be +4 or -4. They could gain 4, 1, 2, 3, 4, negative, or they could lose 4, 1, 2, 3, 4. So these are + or -4. They're going to be driven most by what's near it. These would be -3, this column here, because it's going to lose or gain 1, 2, 3 electrons. This column would be -2. This column would be -1, and these guys do not have a charge. Again, if this is a bit confusing, go back in some lessons where we kind of focus on this a lot more. And like we were just showing you guys, the halogens, or the second to last group, group 17, were all -1. So fluorine becomes fluoride when it becomes an ion. Elemental chlorine becomes chloride. Bromine becomes bromide. Iodine becomes iodide. Notice we take the last syllable off and we add IDE. And just to look at that again, we're talking about this family right here. These guys all become -1. Oxygen and sulfur become oxide and sulfide, and that's -2. So let's take a look over here. And yeah, let's take a look at that. Oxygen and sulfur become -2, 1, 2. And finally, nitrogen becomes -3. It has to gain 3 electrons to get a stable configuration. So see here, nitrogen would be -3, 1, 2, 3. So these are things that you really need to understand when we're building into this stuff. So we're talking so far about main group elements, which are the S block and the P block. Because they're very consistent in their electron configuration, we can predict them. Notice I skipped here the transition metals, but with a little bit of insight on the transition metals and what we've learned, we learned that the electrons fill, like let's talk about right here, we have 4s adds 2, and then this is not 4d, this d block here, it's 3d, we fill into the core. So if we have the 4th shell has 2, and then we start filling into the core, you might reasonably think that the transition metals, when they become ions, should all lose 2. They would lose these 2 and go back to a noble configuration. So we lose 1, 2 to here. It doesn't matter where you are in here because it's got these 2 in the outer shell, the 4th shell, where this is the 3rd shell. And that is very good reasoning, but it's not the whole story. And this is why transition metals are not main group elements. They do behave a little strange. If you take a look here, main group elements can have, like here's copper. Copper can be 2, but copper, notice this, copper can also have a charge of 1. Iron can have a charge of 2, which makes sense, but it can also have a charge of 3. Nickel can be 2 or 3. So we have these different situations here. And look at titanium. It could be plus. It could be a 2+, a 3+, or a 4+. So there's a lot of variation in the possible charges that a transition metal can have. Sorry, my nose is all plugged up. Got the winter cold right now. There's a lot of variation here on what the transition metals can be predicted as charges, and this is why they are not main group elements. So when we have transition metals, let's go back here. They're named with a Roman numeral, so copper 1 or copper 2 with a Roman numeral, and that Roman numeral is very helpful because it's telling you the charge. So copper 1 has a Roman numeral 1, copper 2 has a Roman numeral 2, iron 2, iron 3, that's the charge. So let's look at titanium. This is the Roman numeral for 4. So titanium 4 means that titanium has a positive 4 charge. That's the titanium we're talking about. When you are making or naming ionic compounds and there's a transition metal involved, you must include this Roman numeral. You must include which one it is because transition metals can have multiple charges. So if you have a transition metal, you need to indicate it with these Roman numerals. Sometimes, most of the time there's Roman numerals, and we're moving more and more to the authors are moving more and more to this Roman numerals, but sometimes they're named without the Roman numerals. In this case, of the choices, the one with the small choice is going to end with us, and the larger choice would end with ic. So if we take a look here, copper, the small choice is +1, and then the large choice is +2. But with iron, the small choice is +2. So don't think that small us means 1, because it doesn't. There is no 1 for iron. It's of the possible choices, the smaller one is us, and the larger one is ic. So this might actually help you understand too some of the strange letters on the periodic table. The small version of iron is called ferrous. That's iron 2. Iron 2 is ferrous. They both interlinked. You can use either. The reason I talk about this is I like my students to know if they, because sometimes on labels and stuff you'll see ferrous or ferric, and I like you guys to know what that means. So ferrous is iron 2, ferric is iron 3. Cuprous is copper 1, and cupric is copper 2. So that's the smaller choice and the larger choice. I find it, I have memorized that iron can be 2 or 3 and copper can be 1 or 2. But after that, to figure out which one's ferrous and ferric, it's very easy to forget. But I have this one way that I like to remember, and hopefully I know it's an old movie now, but hopefully you've been exposed to this fantastic old movie. It's Ferris Bueller's Day Off. And in Ferris Bueller's Day Off, if you haven't seen it, it's about a kid that seems to get away with anything. He's always comes out on top. He's always first. He ditches school. He gets away with it. He goes into a parade. He ends out singing in it. He's just got a charmed life. So Ferris is always first, Ferris Bueller. So Ferris is always first. It always comes Ferris and then ferric. And if you can remember Ferris is always first, then you would remember that copper 1 would be cuprous because the us is always first. So hope that helps. That's the way I remember it. You can do any way you like to remember it. Hopefully whatever you figure out works for you. Okay, so let's look at their transition metals. I'm going to talk about why transition metals have these strange configurations. And to do so, we're going to talk about titanium. So let's look at our periodic table. And I'm just going to start on the third row here. So for titanium, titanium is right here. It's number 22. And so on the third row, we'd have 3s would fill up with 2. And if you don't know what this is, please go back and watch some older topics because this foundation is really important to understand what's going on here. So electron configurations are what we're doing here. So to get to titanium, I'm just starting. There would be a 1s, 2s, 2p. Then we go 3s, 3p, and then 4s, and then remember it's 3d, and we'd have 2 in the 3d. So if we take a look here, we would put 1 in the, we'd fill it up like this, the 3s, and then the 3p fills up, and then it doesn't go to 3d, it goes up to 4s. It fills up 4s, but 4s is higher energy level than 3d, and these next 2 electrons fill into the core. So the transition metals are going to do just what titanium does, and they're always going to have 2 valence electrons, meaning 2 outermost electrons. So titanium, if you remember back at the notes we were just talking about with the possible charges, titanium has a possibility of being a charge of +2. And if you think about the 2 electrons that would be removed, they would be probably the 2 outermost. And I mentioned before, transition metals, you would predict them to have a +2 charge because these 2 would be removed. But titanium can also have a +3 charge or a 3+ charge. And so what will happen here is D has higher energy than P. So electrons from the d orbital sometimes can be taken away as well if there's something electronegative around it. So sometimes you can get a positive or 3+ charge by removing these 3. And if you can remove those 3, I think it makes sense why we would understand that titanium can have a 4+ charge. It would remove all the electrons from the 4s and all of them from the 3d. So we have these possibilities with titanium, titanium 2, 3, and 4. Let's look at another example, iron. Iron has this electron configuration. It has 1, 2, 3, 4, 5, 6 electrons in the d block. So it's right here. So it's got, here's the d block, 1, 2, 3, 4, 5, 6. It's number 26. So this is why we have this electron configuration here with 6 here. So it fills up in that 4s and then 6 into the d. So iron 2, hopefully you understand by now that it's going to lose those 2, and that's what we would predict for all the transition metals. But for iron 3, if you didn't do the electron configuration, you may not quite understand why you would predict iron should have a 3. Well, these 2 are in the same orbital. These 2 electrons are spin paired in the same orbital. They don't want to be near each other. They're electrons. They're repelling each other. So if you can take these 2, it's not that hard to take another one from iron, and you get a much more stable configuration when iron becomes 2+ or 3+. And I think you can see that right here because now all these electrons have their own orbital, and they're not, these 2 weren't paired up and repelling each other. Let's do one more example. So copper, we'll take a look again at the periodic table. Copper is located here. It's number 29. So we fill up the 4s, and then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 electrons in the d orbital. Here's zinc over here. That's the 10th one. So copper has 9 in that d orbital. So let's take a look at copper here. We've got these 9 electrons here. Copper can get a +1 charge, which seems a bit unusual for a transition metal because it's got 2 valence electrons. So how would it be a +1 charge? Well, let's keep our eye on this yellow electron and see what happens here. When it loses 1, take a look at this. It loses just the one, and another valence electron slides down into this D shell, and you get a very stable configuration here. So copper can easily lose one and get a nice stable configuration. And by the way, this would be cuprous because it's the first choice, the smallest option. And for copper 2, it does the typical, what you would expect, losing the 2 electrons in the 4th shell. And that's copper 2. So I just like you guys to have an appreciation for why the transition metals can have multiple charges. You don't expect it to memorize why they're all doing this, but if you do write an electron configuration, you will probably understand it a little bit better. The next thing is polyatomic ions. Polyatomic ions are kind of like a molecule. It's a connection of atoms that are connected together, and this whole system has an overall charge. So this is an acetate ion. It consists of 2 carbons, 3 hydrogens, and 2 oxygens, and the whole thing has a negative charge. This is the carbonate ion. It's got a carbon and 3 oxygens connected to it, and the whole thing has a -2 charge, or 2 negative charge. So this is just a list of some polyatomic ions. I have a sheet that I will be handing out in class, and I'll also post them on the website here at mrrast.com. And you can look at all the polyatomic ions that you will need to know, because sometimes you'll be reading things like sodium acetate, and you'll have to know what acetate is. It's not on the periodic table. I'm sorry, it's not fun, but you have to memorize these polyatomics. Chemistry, I say to my students quite often, it's like a math class, science class, and a foreign language. And right here is that foreign language. You have to be able to see this C2H3O2 negative and know that that's acetate. You have to be able to basically speak another language when you're reading this stuff. So you'll see these things and you'll say these things. So you do need to study this, and I do have a study guide on there and a link to some practice tests that you can do. But I think memorizing these polyatomic ions is probably the most challenging part of learning about ionic bonds. So what is an ionic bond? Well, ionic bonds are formed by the attraction between oppositely charged ions. So when you form things like we just talked about at the very beginning of this video, sodium being plus and chlorine being negative, chloride, what happens is sodium gives an electron to chloride, and when doing so, it makes the sodium become a sodium ion that's positively charged, and the chlorine becomes negatively charged, and opposites attract. The positive and the negative attract to each other. And what's important to note here is that when they come together, they're ions, but when they come together, the compound, the ionic bond between them two neutralize the charge. Sodium chloride is not charged. It's made of charged particles, but itself is not. It's not a charged molecule. It's not an ion itself. So they neutralize each other, these charges, the positive and the negative, and then you get sodium chloride. So when you write an ionic structure, a formula, do never put those positives and negatives. As a teacher, it's really easy to grade wrong ones, because if I see a negative up here and a positive here and you put them together, it's wrong. There will be no superscript of charges. So please remember that and don't do that. Don't make my life so easy to grade yours to see that there's all kinds of problems with it. So notice, these charges disappear when the bond is formed. All right. So let's talk about this. How do we write ionic formulas? So we're going to practice right here with aluminum fluoride. The first thing you need to do when you write a formula is write the symbols for it. So the symbols for aluminum fluoride are Al and F. We find them on the periodic table, and like I've talked about before, we have to write the charges. You have to write the charges. So aluminum is +3. And you can go back a little bit if you're confused on why it's +3. And fluorine becomes fluoride, which is -1. You should be looking at your periodic table when you do this. And aluminum is +3. It's right here. This column is +3. And fluoride is -1. Anything in this column is -1, and this column is +3. When you write ionic formulas, the cation is always first. That's the positively charged one. So it's always first. Its Al will always come before the F because that's the cation. The next thing you do when you're trying to figure out the formula, remember they neutralize each other. Aluminum is a lot more positive than the fluoride, so you got to try to figure out how to make it balanced. A textbook definition of it is find the least common multiple. So what's the least common multiple between 3 and 1? The least common multiple between 3 and 1 is 3. So if we take a look at aluminum, its charge is 3. 3 goes into 3 how many times? And the answer would be once. Fluoride has a charge of 1. 1 goes into 3 how many times? It would take 3 of them. So therefore it would take 1 aluminum, because 3 goes into 3 once, and it would take 3 fluorides to make the structure. Aluminum fluoride would be AlF3. That would be the structure for it. I want to show you a couple different methods of doing this. A couple different methods for figuring out the charge, and I'll use my handy notepad that always seems to aggravate me. Okay, so let's take a look here. So aluminum, we knew that was +3, and what you can do is just put 3 pluses on here. And fluoride has a -1. These two, this positive and negative, will neutralize each other. But you see there's still some positive left over. So we have to have, or we can add another fluoride. I'm sorry, I cannot stand this thing. It just jumps around all over the place. So that's another negative. And this positive and this negative will neutralize. And then we have another fluorine. Why does it shoot around like that? Okay, we got another fluorine. And that's negative here. And this will neutralize here. So it would take 3 fluorines to neutralize the aluminum, so that it would mean there's 1 aluminum, and it took 3 fluorines. That's another way of visually kind of looking at it. And the third way you can do this is you take the aluminum's charge, you take Al3+, and the fluorine's charge, negative, and what you do is you take these charges here, you take that value, these two values, and you cross them. You bring them down to the denominator. So that would mean that and you get rid of the charges because they're neutralizing each other. So that would mean how many aluminums are there? Where there's just a 1 here, so it's just 1 aluminum. And how many fluorides are there? Well, it's going to have 3 of them. The only trick that you have to remember with this method is you have to reduce. So I'm going to give you an example of what I mean about simplifying. So if we look at calcium oxide, and we do it in those 2 different methods, calcium has a +2 charge, so we would write 2 pluses. And oxygen has a -2 charge. And you can see that this positive and negative cancel, and this positive and negative cancel. So to neutralize each other, it would just be simply calcium oxide, CaO. But if you cross, and you don't pay attention here, you might cross these values down here. And if you just bring the 2's down, you might write it Ca2O2. It needs to be simplified. This is not the proper way to write calcium oxide. You would need to simplify it and see that 2 goes into 2 and they reduce each other to calcium oxide. So that's what I mean about simplifying. Okay, so we're practicing naming. Can you name this compound? Well, think about it. It's a Ferris wheel. Ho 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 ho! All right, let's go more of this visual thing. I do a little game in class, but I think you'll get the gist of it, and I'll go over all the answers with you right here. So we're going to make calcium fluoride. We cut out little pieces of paper here, and if it's a charge of 1, I make it a smaller piece. If it's a charge of 2, I make it a little bit bigger pieces, showing these 2 positives. And if it's a 3, I have 3 of them here. And I go, so these are cations and these are anions. And so to make calcium fluoride, what we would do is we would add a cation, calcium, and we'd add a anion, fluoride. And to be a stable compound, it has to be a 4-sided object. And right now, this is 1, 2, 3, 4, 5, 6-sided. This is not a 4-sided object. This would not be a solid configuration. So if there's one calcium, there's going to be lots of calciums. And if there's one fluoride, there's going to be lots of fluorides. So therefore, to make it balanced, to balance out that 2 charge of calcium, it would take 2 fluorides. So the correct ionic formula for calcium fluoride would be CaF2. It took 1 calcium and 2 fluorides. Note that for every 1 calcium ion, there must be 2 fluoride ions. So what we do here is I have students work on this together, and they build these with me, and I go around the class and I help them. But for you, I'm going to just go through these real quickly and show you the answers to them. So we're going to first build sodium fluoride, and to do that, there we go. To build sodium fluoride, sodium is got 1, and fluoride, if you look on the right side, is -1. We have a negative. And so these guys just match up perfectly, so sodium fluoride would just be NaF. Cesium oxide, okay, what's the charge of cesium? Cesium is CS positive. Notice I make the S cursive. If I write if you write your cesium like this, C and then an S, it can be very easily confused as carbon and sulfur. So what I'd like you guys to do is think of these as symbols and not just the alphabet. Make your S's cursive. Make your lowercase letters cursive. Print your uppercase letters, because this can easily be confused as carbon sulfur, as chlorine could be easily confused as carbon and iodine. So chlorine should be written like this. Okay. So don't write it like this or like this, please. So cesium is positive, and we're combining that with oxide. Oxide is -2. So we have oxygen, and it has 2 negatives on there. And therefore, to balance this out, I would have to add another cesium. Now it balances out, and we have the structure. So this would mean it would take 2 cesiums and 1 oxygen. Cesium oxide would be CS2O. Aluminum hydroxide, take a look at that. Aluminum hydroxide, aluminum is a +3 charge. So aluminum, and again I'm making a cursive L because it is lowercase, and it's got 3 positives. And hydroxide over here, it's a polyatomic ion, OH negative. So hydroxide would be OH, and there's a negative. That cancels, but I'm going to have more hydroxides so that all the positives and negatives match up. So therefore, aluminum hydroxide would be written like this: AlOH, and there's 3 of them, 3. Students might write it like this. This is actually incorrect the way it's written. You might make sense, but what this is saying here is I have 1 aluminum. That's true, I have 1 aluminum, and I have 1 oxygen and 3 hydrogens. But the reality is I have 3 oxygens, don't I? I have 3 hydroxides. So just like you do in your math class, you put parentheses around things. And now this says I have 1 aluminum and I have 3 hydroxides. All right, guys, let's do cupric nitrate. Let's do cupric nitrate here. So to do cupric nitrate, we have to remember cupric would be, is that the small copper or the large copper? Well, remember ferrous is always first, so us is first. So it would be the larger copper. So it's not copper 1, it would be the copper 2. I put them in black so that you can kind of keep your eye on these 2 possible choices for copper. So this would be copper 2. I don't know why that went all crazy like that, but of course it's just because it hates me. Let's see here. Okay. All right. So cupric nitrate. Nitrate here is NO3. So NO3. NO3, and it's got a negative charge. So that would mean we would need another NO3 to balance this out. And now that it's balanced out, it would be Cu, 1 copper, and there would be 2 nitrates. So that's nitrate would be happening 2 times. So don't forget these parentheses, very, very important. Cuprous carbonate. Let's look at cuprous carbonate together. Cuprous carbonate, that would be the smaller copper, so that's copper 1. So cuprous carbonate would be, where are you? Cu1, and carbonate would be CO3 with 2 negative, right? Carbonate, CO3, 2 negative. And so we would need another cuprous. Now they balance out, and so the formula would be Cu2, we have 2 of them, and carbonate, CO3. I don't need parentheses around this time because there's only 1 carbonate. Hg2, and it's got a positive 2 charge. And sulfite. Sulfite is SO3, and it has a negative 2 charge. You see these guys balance each other out. They cancel each other out. So it's a 1-to-1 ratio, and we would write that as Hg2SO3. Okay? That was... Let's do calcium phosphate now. Calcium phosphate would be written with calcium. Calcium as a +2 charge. And phosphate is PO4 with a -3 charge. 1, 2, 3. Well, these guys are canceling each other out, but it's still got a little bit more negative. So I'm going to add another calcium. Calcium always have to, when I add the calcium, I always have to add 2 pluses. So now that's here. Now I've got a little bit more positive left over, so I'm going to add another phosphate. And phosphate always has to add -3. So these guys cancel out. So I still have some more negative, so I have to add another calcium. And these guys cancel. So for everything to cancel, for the calciums, remember, here's a calcium right here. Here's a calcium here. And here's a calcium here. And here's a phosphate. Remember, it's -3. And another phosphate. That's -3. So it takes 3 calciums. So this one matches here. This one matches from here to here. And then we got situation here. So it takes 3 calciums to match the 2 phosphates. So the formula for calcium phosphate would be Ca3 parentheses PO4. And how many phosphates do I have? I have 2 of them. All right. Our next guy on here would be cesium fluoride. This one's a lot easier, cesium fluoride. If we take a look over on the left, cesium has a charge of +1, and fluoride has a charge of -1. So cesium fluoride should be a nice, easy one for us to do here. Cesium fluoride should just be CS+ and a fluoride. These guys are 1-to-1 match, so cesium fluoride would just be there. And that would be cesium fluoride. Let's go to aluminum. Aluminum nitrate. Aluminum nitrate would look like this. Aluminum has a charge of +3. 1, 2, 3. And nitrate, NO3 negative. So I would need 3 nitrates Good grief. 3 nitrates to match up with 1 aluminum. So it would be just aluminum and nitrate 3 times. It just doesn't write all the time. It's funky. Sodium and hydroxide. It's just a 1-to-1 match, so it would be written as NaOH. And mercury phosphate, mercury 1 phosphate. This is a tough one. This is a tough one because I think a lot of people make a lot of mistakes on this one here. So let's look at mercury 1 phosphate. So mercury, come on, right, pen, right. Just, you know, it just doesn't write. So glad I spent money on this thing. Mercury 1 is always like this, right guys? Mercury 1 is 2 mercuries with a +2 charge. And phosphate is always PO4 with a -3 charge. So again, we've got these guys matching. That's the third one on the phosphate. So we're going to have to add another mercury 1, which is another +2. That matches with this one. I'm going to have to add another phosphate, which is another 3. That one could go there. I have to add another mercury. So what happens is for 1, 2, 3 mercuries, it takes 1, 2 phosphates. So when we write this one, this is an interesting one to write. We have to say mercury, and a lot of people get this wrong. It's, oh, and I actually did it wrong. Take a look. It's mercury 1 has the subscript 2 there. So we have mercury 2, or mercury 1, we have that 3 times. So we got to write that like this. And we have phosphate twice. So write it like this. This is a good one if you've been watching the video and suffering as I have with the pen. This is a good payoff to make sure. This is a tough one. So that's how you write this one here. And then our last one that we're going to do is aluminum sulfite. Where's my pen? Aluminum would be 1, 2, 3. And sulfite is SO3, -2. So I'm going to have another sulfite because I got too much positive over there. 1, 2. These guys match, these guys match, these guys match. Have to have another aluminum. 1, 2, 3. This one matches up, so another sulfate. 1, 2. So for this to match up, aluminum with 3s, +3s, matching up with sulfites with -2. It's going to take 2 aluminums to match up with 3 sulfites. So just hopefully you pause the video or come back to this and try to work them out and check your answers with mine. Don't forget these parentheses and all those superscripts. Notice there's never subscripts. There's never a superscript and there's never a charge. If you're doing that, you're doing it wrong. Okay, this is the workshop that we're going to be doing in class. And in these ones here, you're going to have to write the formula. So potassium bromide, you would have to write it out. I'll give you the answer to this one. That would be KBr. It's a 1-to-1 ratio. Potassium is +1 and bromide is -1. And then over here you name them. So this would be lithium bromide. I'm going to put a link on the website. So if you're looking at this at mrrast.com, all the answers to these will be in a workshop, a Quizlet that I'll have linked here, and so you can practice these things. When you do the Quizlet, I highly recommend you use it to practice this workshop. Don't do it so much that you're just memorizing, that you're just looking at LIBR and just saying, oh, that's... as soon as you see the Li, because notice there's how many lithiums are here. There's only 1. So every time you see the lithium, you just go, it's lithium bromide. Don't set it to memorization. practice it. Every time you do it, practice it. So I know on Quizlet sometimes I do like matching and stuff like that. Don't do those ones. At least I don't recommend it. I would do the ones that you actually fill it in, that you actually have to write and guess. Practice the index cards to do that. But these are good index cards questions, guys. Hey, write potassium bromide on one side and put KBr on the other. If you can go back and forth, that's really good. So give this a try. We'll do this in class, and we'll do some more practice in class. And bring those questions to class, because if you have any problems, that's what I'm here to help you with. So please take advantage of that. Good luck and happy holidays.